Having looked at how to interpret the printed output from linear regression, let's take a look at the linear model that the function LM generates. There's a lot of useful information contained in that model. So in this lecture, we'll take a look at how to use that particular model or object. Now, in this lecture or in this lesson, I'm using the model that is generated. In fact, the model is going to be built without any data partitioning or anything. This, of course, you understand is for illustration purposes only. So we are not using data partitioning, but that's only for this lecture. When we are using it in the context of predictive analytics, we will always do partitioning. Okay, so don't take the fact that in this lesson we are not doing partitioning as anything illustrative of what you should be doing, because the purpose of this lecture is only to illustrate what information is contained in the linear model object that is generated. Okay, so here's an example that you used earlier, a file called mlr example.csv, and it's got information about rooms and house prices and so on. So what we're doing is building a linear model for predicting the price based on all other attributes in the dataset. And then we do summary h.lm to get all the information that is contained in this linear model. So there are three predictors, rooms, area, age, and the target attribute, of course, is the price. So those are the four columns in the dataset: rooms, area, age, and price. And when we say price tilde dot, we are saying generate a linear model to predict price based on all of the other attributes, which happens to be these three. And of course, you get this regression model. You've got the coefficients. It turns out that only area is significant. The other two are not significant. We're not going to worry about significance for this particular example, because all I'm trying to do is to show you what information is contained in this h.lm variable. That's the linear model. So we want to see everything that we can extract from it. Okay, so if you do str h.lm, you're going to see a whole bunch of stuff. This, of course, is dizzying. We will learn to use some of this information. Okay, so don't try to go through this and try to make sense of it. I'm just showing you that this object h.lm is packed with a lot of information. First of all, let's see how we will compute the total sum of squares. So of course you know that total sum of squares is nothing but the total of the squared deviations from the mean. So price is our target attribute. So first thing we are trying to do is to calculate the mean of that. So mean $h is going to give us the mean price, which I'm storing in a variable called m_p. Okay, and that happens to be 251,941.2. So now we want to calculate the total sum of squares, which is nothing but h price minus m_p, which is the deviation from the mean. Now notice that h price is a vector, m_p is just a single number, but r is going to do vectorization and treat it as if it's a vector of the same size. And it's going to calculate the deviation from the mean for each of the price values, square the deviation, and add up all of those squares. Okay, so this is your sigma that you see in the formulas, and that gives us the total sum of squares, which happens to be this. Now incidentally, in the first linear regression exercise assignment, I had asked you to compute all of these things. So I'm just re-emphasizing the same ideas. Okay, let's see how we can now compute the predicted values. So this was just calculating the total sum of squares. Now how do you compute the predicted values? This first method is just for illustration purposes. You don't have to do this. So here what I'm doing is I'm finding out the regression coefficients, which are of course in our regression model. Okay, so here are the regression coefficients. For rooms, this is the intercept, and for rooms it's 190, etc., etc. So these are your regression coefficients, and we can use all the regression coefficients to calculate the predicted values. So this is what it is, and then we are saying, of course, incidentally, the coefficients, we could look at the output and then create this vector of coefficients, or alternately, we can just do h.lm dollar coefficients. So this model object has a field called coefficients, and that will directly give us the vector of coefficients. Okay, so that's a useful piece of information contained in the model itself. So you can either compute the coefficients by manually looking up the output and then typing it in, or do it the easy way, h.lm dollar coefficients. So no matter how you got the coefficients, you can calculate the predicted value as coefficients of 1, which is the intercept, plus coefficients of 2 times the number of rooms, 3 times the area, and it should be 4 times the age. So that's going to be your predicted values, right? Of course, all of these are, h dollar rooms is a vector, area is a vector, so the result is going to be a vector. So predicted is going to be a vector containing the predicted values for the same data that we used for building the model. The better way, of course, is that the linear model object that we built actually contains the predicted values directly. So you just have to say h.lm dollar fitted dot values. That's a field which is in the linear model, which already contains all the predicted values, right? So there's really no need to do all of this. I did this just to show you, to give you some understanding of what is contained, so that you understand what this fitted values actually contains. It effectively contains this. Okay, so this computation has already been performed for us. The result is already available in the linear model. Okay, of course, this result is available only for the data that was used to build the model. It's not available for any new data. So if you have new data, then you have to use the predict function on the new data. Okay, now let's go ahead and compute the residuals. Once again, I'm going to show you the long way, and then of course you can guess at this point that the residuals are also contained automatically in the model itself. Okay, so we've computed the predicted values using one of the approaches that I showed here, either by the long way or by the short way, just by plucking them out. Once you have that, you can then say residuals is nothing but h dollar price minus predicted. Okay, the actual value minus the predicted value, that's the residual. Alternately, of course, we can just pluck it off from the model itself, h.lm. h.lm, or any linear model, has a field called residuals, and that field contains all the residuals. So you could just say res is h.lm dollar residuals, or any linear model that you, any output of the lm function, dollar residuals, you get all the residuals. Now once you have that, you can compute the sum of squared errors is nothing but sum residual squares, squared, right? Because this is the residual is nothing but the error for each case. You square it, add it up, and you get SSE. And that happens to be so much. Now you want to compute the sum of squared regression, which happens to be the predicted value minus the mean squared sum of that. That is sum of squared regression. You can look at the equation that we had, right? Because the sum of squared regression is nothing but what is predicted, right? So it's telling us, the regression is telling us that the predicted value is going to differ from the mean by so much. Okay, so this is the amount of variation explained by the regression. So that is your sum of squares regression. Now with all of that, we can now compute the r squared, right? Because we've got the sum of squared regression, we've got the total sum of squares, we can compute r squared. Sum of squared regression divided by TSS is r squared. It comes out as 8335. And if you look at the regression output, it says 834. It's just been rounded off to 3 digits. Okay, so that is the number that you're seeing here, and this is exactly how this number is calculated. Now one thing you will note in this course is that I'm showing you the output that R generates, and for the most part I'm showing you precisely how each of those numbers is actually calculated, right? So that when you look at the output, there's nothing greatly mysterious going on in the output. Okay, I've tried to explain to you not only for the linear model, but for all of the other things we have done so far, I've tried to explain to you how exactly each of those numbers is obtained. In other words, what does that number mean?